As we move forward talking about electrochemistry, we want to talk about some applications of these reduction oxidation ideas. We're going to start with is talking about titrations. So we know that a titration is just a process to determine the concentration of an unknown solution. And this is a really useful kind of analytical tool that we have at our disposal in the chemistry lab that we've seen previously for acids and bases. And so when you're wanting to do a titration, you need to be dealing with a chemical reaction. And that chemical reaction needs to be known. You need to know what the chemistry is. And what that means is when you mix two reactants, what products you're going to make. So you need to be able to predict the products without actually doing the reaction. The reaction needs to have really fast kinetics. You don't want to be worried about having it take hours or even minutes to react. You want really, really fast kinetics. You mix the solutions together, boom, you get product. And you want very product favored equilibrium. Basically what that means is you want to use stoichiometry. You don't want to worry about an ice table to figure out the amounts of product. Just you mix some reactants, they react really quickly and they make product. So you can use stoichiometry, all that sort of stuff. And so acid-base chemistry checks all of these boxes, because it's a Brunstad-Lowry acid that allows us to predict the product, that shift of the H+, really fast kinetics because you're just moving the H+, and very product-favored equilibrium. Basically, we use a strong acid, strong base. We are pretty much guaranteed that, this is just going to go all the way to product. We're not going to have to worry about ice tables. We can just use stoichiometry. Redox chemistry also works. It's a little more complicated. You got the half reactions and balancing, but if you know the half reactions, you can figure out what they're going to do. It is harder to predict products, but we're just going to go from that. If we know the half reactions, we can balance. Redox is very fast and it's very product favored as well, which we'll see in a later bit in the chapter. So when you're wanting to do a redox titration, the overall idea of the experiment is very similar to the acid-base titrations that we've seen previously. You have, you pick a titrant of a known concentration, you fill your burette with that. So, we have this purple solution that's up here in the burette, say KMnO4 in this particular reaction. You add enough of the titrant stuff out of the burette into the flask until you reach that equivalence point that we've seen previously, which is when all of my analyte has reacted. Whatever I'm analyzing, the solution I'm actually analyzing, all of the moles in there have reacted. I determine the moles of titrant that I added. I use stoichiometry to relate that to the moles of analyte. And then I determine the concentration by dividing that moles by volume. So that's the overall kind of process for doing titrations that we saw for acid-base chemistry. And functionally, especially on the analysis side, once you get your data, it's going to work very similar to the acid-base titrations we've seen. It'll work through it in a similar way. There are differences when you're doing redox titrations, but they mostly come up with how you actually functionally do the experiment. One, and most importantly, stoichiometry is not always one-to-one. With acids and bases, the stoichiometry was always one-to-one because you always have that transfer of the single H+. You will notice these coefficients in this redox reaction are not all ones. In fact, they are very non-one. And so you're going to need to account for that aspect when you're doing the titration or when you're doing the analysis. When you're actually doing the titration, choosing a titrant is more complicated. We will talk a little bit about it, but in acids and bases, you just chose, if you had an acid, you chose a base. If you had a base, you chose an acid and you just chose a strong one, right? So always use HCl or NaOH and you're good to go. It's a little more complicated when you're dealing with redox reactions because you need to figure out what sort of chemistry is going on. When it comes to indicating the equivalence point of knowing when you've reached the equivalence point, there's also some complications with that. There's multiple ways to do it and different redox titrations, different sort of actual experiments, certain indications of the equivalence point will be better as opposed to acid base where you could always look at jumps in pH or color change for indicators. Also, there's usually other compounds in there. There's a little more kind of other effects that you need to put in, namely, generally, you're using a lot of acids that are just kind of affecting the chemistry as opposed to driving the chemistry. They're not doing the reaction, but they're kind of affecting the reaction, kind of like a catalyst or things like that. So there's a little kind of other factors, other kind of flavors, spices to affecting this that we'll talk a little bit about. So when you're doing a titration is when you have a situation where it's like, what is the concentration of this platinum 2 chloride solution, right? I got this solution right here, okay? What is the concentration of it? If I didn't make it myself, I don't know. Or if I used like a really crude measurement, I just poured like, it's about a gram in. I want to know what exactly the concentration is. And titration is almost always going to be our tool or our process for answering that question. Thing is, platinum 2 chloride, that's not an acid and it's not a base. So I can't use acid-base titration. I'm going to need to use redox chemistry. And we're going to see that you get away with redox chemistry, using redox chemistry a lot. You can generally do that. There's a much wider applicability than when it comes to doing acid-base titrations, which you're fairly limited on. So what do you use as a titrant? What do you use as an indicator? How do you do this experiment? So those are the questions we want to be able to answer, or to at least think about and understand the answers that someone may provide. And so that's what we'll talk about over these next few videos, looking at redox titration. First, a video down in the set. Redox titration is going to be the bulk of what we're talking about today. Participation 11.7 is our participation segment. No questions in this first video, but I got plenty more in this set, much more details of titrations to look at. Week homework due Saturday, redox titration post lab due Sunday. I would encourage you to watch the videos before you try it. If you have any questions about anything, let me know. Otherwise, see you in the next video.